Hello everyone. Today I have a project I assumed would be quite simple, but I ended up chasing my tail for a good while before coming to the correct conclusion. We're going to be building a die holder for the lathe, which mounts in the tool post and is powered by the main spindle. However, before I start building and testing, we need to take a look at the design of the die holder. But before even that, we have to take a look at the dies themselves. Threading dies are form tools that cut the exact profile into a piece of stock to form a thread of a certain size to its given tolerance for any length you could want. Pretty much the same as a tap, just inside out. If you're into metalworking, you will likely know that for each size of thread there are different kinds of taps. The same is true for dies. They are not all created equal. There are three main factors that differentiate a normal tap or die from an industrial grade one. The first is material. There are numerous different kinds of high-speed steel. The most common high-speed steel is marked as M2 and will usually be marked simply as HSS on the tool. Now there is something better out there, which is M35 high-speed steel. Marked on the tool is HSSE or HSS-CO. This M35 high-speed steel has cobalt added to the steel alloy. The cobalt increases its hardness a little bit, but greatly increases its temperature resistance. And it's this temperature resistance that allows the M35 alloy to cut faster and last longer than the M2 alloy. For us, that just means the M35 will last longer. It's not like we're threading with dies at 1000 RPMs. The second factor is cutting geometry. Let me start the comparison with taps. Those are more intuitive. Cheap taps have straight flutes. This means the shavings can pile up in the flutes and can potentially jam up the works and damage the threads or break the tap. There are two very clever solutions for this: spiral point and spiral flute taps. They both push the chips away out of the cutting area. The spiral point pushes them forward deeper into the hole, and the spiral flute pulls them back out of the hole. If you plan to do any kind of power tapping, please get spiral point or spiral flute taps. I have a hot take to share with you. Spiral point taps are the best taps for manual machining. They are the strongest and give the best results. Spiral flute taps are weaker and should be reserved for deep blind holes that need to be tapped to the bottom. I try to avoid buying normal straight flute taps when I can help it. Before we get sidetracked too much, let's bring it back to the threading dies. If we compare these two, we can see that there are some little scoops taken out of the front of the black one. That extra angle pushes the chips back out of the cutting zone, so it's basically a spiral point die, also called a gun-nosed die. In my opinion, if you want to thread with these under power, a spiral point die is a minimum requirement. The third factor is coatings. Most dies are not coated because they are not expected to operate at high speed. This one here does have a coating which is advertised as a VAP coating. I haven't been able to find out what exactly that is, but I suspect it's some kind of black oxide coating which helps the surface hold onto cutting oil. The high-performance tools are almost always coated with some kind of ultra-hard layer. It's been well established that these coatings can provide big productivity gains to tools like end mills, drills, turning and milling inserts and taps, but the advantages to a hobby machine shop are debatable. To summarize, if you're looking to use threading dies in your machine under power, I would recommend getting a spiral point die made from M35 high-speed steel. With dies like that, you can cut threads in most materials, including high-strength alloys up to 1000 megapascals tensile strength, which is found in metals like heat-treated 4140, aka 42 chromoly 4 plus QT. When I screw this bolt into the die, we can see that the die is basically captured in all degrees of freedom in relation to the bolt, except for the singular helical path which follows the pitch of the thread. When using the die by hand, the die will guide itself as long as we don't do something stupid and force it to cut crooked. When we put the die into a machine where it is held rigidly, we have to be mindful of these constraints. It's obvious that the die has to be in perfect alignment with the spindle center line, but what may be less obvious is the axial guidance. The die needs to be able to follow the screw lead it is cutting into the material exactly. When the die is cutting, it experiences a torque from the part it is cutting the thread into. This torque has to be counteracted by the holder. Otherwise, the die would just spin around and there would be no cutting. So we build a reaction arm into the holder. In my first design, the reaction arm is simply a pin in the slot, but it turns out that this may cause a lot of friction. So under working torque, this friction is created, which imparts a drag onto the die while it is cutting. This has the potential to influence the pitch of the thread we are cutting. So with the benefit of hindsight, I can already tell you that the design with the sliding pin has the potential to go wrong. I have some horrendous test pieces that I will attribute to excessive axial friction. This friction can be mitigated by good materials and excellent craftsmanship, or by further improving the design. For craftsmanship, I will refer you to Swap Lamp, a Japanese machinist on YouTube who has made this design a long time ago, and I want to credit him with the inspiration for my build. His version uses high quality materials and he is able to make very smooth surfaces which reduce the friction of this mechanism. His tool seems to work very well. My tool, on the other hand, did not work quite as well in this first iteration. I used hot rolled steel that does not lend itself very well to fine finishing. It's very soft and scratches itself very easily. But there is another solution. If we cannot achieve low friction by ourselves, we can insert standard components that have low friction built in. Yes, dear viewer, we are going to install ball bearings into this die holder. In order to do that and have it work correctly, there are some things that need to be modified. I have a cross section here, so let's go over the design. First of all, it's completely through bore, so in principle there is no limit to how long of a thread you can make with it. The shank in orange is clamped into the boring bar holder on the lathe and holds the carrier shaft in blue. The carrier shaft has a standardized mount on the left side to accept die adapters in green. For every size die I have, I can make a die adapter. In order for the bearings to behave in the way that I want, I have devised the following working principle. The tool is now shown in its completely collapsed position, where it should be when starting the cut. In this position, the shank has a nice fit over the carrier shafts and locates the die accurately in its starting position. Face contact ensures the die starts straight, so in the first few revolutions of cutting, the die should be pushed against the workpiece. When the cut has progressed a few revolutions, the shank can stop applying pressure. After the first 2 mm, the carrier shaft is relieved, so it floats freely in the air, letting the die itself decide the alignment it wants to follow. The carrier shaft is no longer making contact with the shank directly and thus no longer causes friction. The torque is transferred through two opposing ball bearings riding in slots, which cause minimal drag on the threading die. The slots in my case are only 30 mm long, so when stationary this tool can cut 30 mm long threads. Of course, during the cut you can move the holder along with the cut and make the threads as long as you want. I like to use the threading lead screw set to the pitch of the die and have the holder follow the die along its travel automatically with the bearings in the middle of the slot. I have this large bar of hot rolled steel laying around that I want to build this die holder out of. My bandsaw is pretty small, so I decided the best course of action is to slice some pieces off in the lathe. This bar is pretty long, so the end has to be drilled for a center to support the end. Cutting the first piece, I'm stopping here and there to make sure the chips are being cleared properly, because it's making some strange noises while cutting. This material turns out to be not very homogeneous on the inside. I'm parting to depth to leave 5 mm at the bottom so I can break these two pieces apart by hand. The second cut I had increased confidence, just at the end I stopped and hand fed the last part to be safe. From the third parting cut onward, I had enough confidence to let this tool cut all the way down in one cut under power feed. Each puck has to be faced and drilled. Easy work, so I won't bore you with all the details. Here's a trick I like to use. Mount the center drill in the tool post and use it as a boring bar to turn a 30-degree chamfer on an existing hole for a live center. Turning the shank on the main body. If you pay close attention, you will see that at a certain point the center is not contacting the part anymore. This is because the feed force of the tool is pushing the part back into the jaws. I suspect this is because the mill scale on the bar is kind of slippery. Luckily, the jaws are set up in a way that I can just push the part back onto a hard stop and clamp it there. That's not going anywhere. I normally don't turn with coolant because it's such a mess, but this time I'm experimenting using small streams that don't reach the chuck jaws to prevent slinging coolant all over the shop. If you carefully regulate the flow rate and position of the nozzle, I found that I was able to use coolant more than I expected, with only a small mess to clean up. To finish the shank diameter of the holder, I'm using a finishing insert that I had good luck with previously. But in this material I was not impressed by the surface finish of the first cuts. In the end I got lucky and landed an acceptable finish on the last pass. This part only has a small portion of the original diameter left, so in cases like this I like to turn from the chuck towards the tailstop, because I don't have a lot of contact with the jaws and I'm worried that the part will be pushed into the jaws like the previous part. To do this is just a matter of plunging the tool into the material at your end point with some tolerance to finish and feed out in reverse towards the tailstop. The tool wasn't chipping as well as I'd liked, and I could tell the feed forces were very high, so I backed off the depth of cut. Now that's chipping much better. The last roughing pass left a horrendous surface finish, so I decided to switch tools and use one of my brazed and lapped carbide tools as a finisher. This tool gave a much smoother finish but still had ridges and bumps in the surface. This material is just not very well suited for precision finishing. The outside of these parts is so rough that rechucking results in a lot of runout, so I had to indicate and tap these back in. That's the price I paid to keep the rough outside preserved for aesthetic purposes. Rough turning the adapter pucks. These will hold the various sized threading dies. This other tool I'm using now couldn't curl a chip very well. These are dangerous chips. Sharp, strong and very hot. At least you won't bleed when you get cut by these. Absolute bird's nest. I was just about to finish turn that diameter, but the camera reached some kind of limit and I don't have it recorded. So you'll have to just imagine some finishing cuts and chamfers happened here. At this point I also realized that I had made one puck the wrong length and one was not made at all. So back to parting more slices of the bar. Time to work on the front of the carrier shaft. I have it in a different chuck that I can indicate and tap around, so now it's all lined up. I want the shaft to be nice and concentric with the bore on the other end. First some chamfers and then bore the receiving hole to mount the adapter pucks which will carry the threading dies. I want this to be a reasonably good fit, so I'm using the new to me internal micrometers instead of the caliper inside jaws. Time to bore out the tool shank. This will be the surface that the carrier shaft needs to fit in. I'm using a carbide shank boring bar to be able to use enough feed rate to try and break the chips in this horrible steel. I'm not sure if you can hear that, but that's a horrible crunchy sound that's caused by chips rolling between the bar and the inside surface of the part. Ideally, I would flood this hole with coolant to flush out the chips while it's cutting, but that would make a big mess since the part is drilled through. In hindsight, I should have probably used the slower spindle speed and a much deeper cut to make big chips that should evacuate themselves better. The finish passes I did with a much higher spindle speed and a shallow depth of cut, hoping that stringy chips would find their way out of the hole before messing up the surface. It ended up with a little bit more clearance than I initially wanted, but I'm glad the bore at least has a nice finish. The shank needs a slot milled for the reaction pin to slide through. I'm starting with the 6mm end mill to rough out the slot and finish with an 8mm end mill. With the carrier installed into the shank, I'm drilling, tapping and counterboring a spot for the shoulder bolt to sit to fulfill its destiny as a reaction pin. drilling and tapping a hole for the set screw which will hold the die holders. I have the carrier shaft indicated into the chuck and mounted the die holder into its place so I can bore the hole for the threading die exactly in line with the carrier shaft axis. This is just insurance to prevent alignment problems later on. Time to assemble it for the first time. The shank slides into the tool block nicely. As I mentioned, the carrier shaft has more play than I wanted, but I don't think it's going to be a problem. There's a good look at the shoulder bolt. They are a high tensile material and have a shoulder with a diameter within a certain tolerance. They are available in different sizes, lengths and tolerance fields. They are not a full 60 HRC hard, but basically the same as 12.9 grade screws, so super strong and tough. The shaft slides around easily. However, I would find out later that under torque, a huge amount of friction would be created and the linear movement would be impeded. Time to test. Let's try easy mode first. Brass. It cuts beautifully and leaves a perfect thread. Brass, however, does not generate much torque when it's being threaded like this. Next, I have some 304 stainless steel. Uh-oh. It stripped out pretty much all threads. What a disaster. Following this, I did a whole bunch of tests, including threading by hand to try eliminate variables. And at the end, I came up with a solution of using ball bearings as reaction arms instead of a pin. To fit the bearings, the slots have to be significantly enlarged and positioned exactly 180 degrees over from each other across the center line of the part. I decided to use my quick indexer and built a support tower to hold the end and add rigidity to the setup. Roughing out the slot with a core drill. The slot has to be 15 millimeters wide, so I'm using a 14 millimeter end mill to rough it out and step over both sides equally to finish the slots. Indexing with this quick indexer is super easy and convenient. It's a Chinese indexer, but it's copied from a hard-hinge model. It needs some refinement, but so far I like it a lot. I'm going to reuse the previous hole for the first bearing, and for the second one, find the orientation for the first one and make a new identical hole with counterbore exactly 180 degrees around the part. I've indicated the shoulder bolt parallel to the table, and now I'm milling a reference flat to indicate on when I position the part for the new hole. Once I indicated it, I just need to find the center of the OD and offset the correct length along the shaft and start drilling. To mount the bearings, I also need some small spacer rings. I'm making them from 42 chromo 4 steel because they are very small, but they will be clamped on pretty hard and I don't want them to deform. I'm using sharp ground tools for aluminium because I want low tool pressure and low deformation. Now to deburr these parts is quite tricky. They are very fragile and just 1.5 millimeters long. A perfect job for the 5C collet block held into the 3-jaw chuck. As a last step, we need to relieve most of the carrier shaft so the bearings can float freely and find their position to transmit the torque without friction influences so the die can do its job. Assembly is tricky because I've made the rings a tight fit into the counterbores and there is not much access to get them in there. But after I get them started, the screw with the bearing will clamp and push it home to the bottom of the counterbore. First test piece is an M5 thread in brass. It's the smallest threading die I currently have, and I'm hoping if there is some kind of unaccounted force or misalignment or any other problem, this should reveal it. No complaints from me. Next I have some nice steel, C45 or 1045 medium carbon steel. This stuff is a little stronger than mild steel, but it's really nice to work with because it doesn't have wild internal stresses. I'm cutting the rods to about 0.1 mm under nominal size. A nice big chamfer, some cutting oil, and lift off. Again, nicely formed thread. On the left you can see where the die stopped cutting, there are some ugly breaks in the thread. That's going to be there with any threading die. It's just a part of how they work. This is a bolt, a 12.9 grade metric bolt to be specific. These are the strongest standardized bolts you can buy. These have a tensile strength of at minimum 1200 megapascals, which makes them about 3 times as strong as mild steel. It's just about the highest grade material this threading die is rated to cut. Those chips are peeling off very nicely. There appears to be a slight amount of tearing at the root of the thread, but the overall form is still very good. This next piece is 304 stainless steel, and I'm going to give you a view from the side to see the bearing doing its work. Now the thread starts showing some defects. Personally, I think it's because of the material. 304 is known to be quite gummy and easily galls. Maybe if I use a heavier cutting oil, I'll get a better result. Or maybe 316 stainless gives a different result? Well, this appears to have even more galling on the threads. I prepared another blank 0.5 millimeters undersized to try and prevent the crest from galling. This certainly galled less, but it's not really the quality of thread I'm looking for. Let's try again, but use a different cutting oil. I dug out my Dormer M200 number 1. I don't use it often because it smells really bad when it gets hot. But the worse it smells, the better it works, right? Well, let's find out. Let's not be shy with the oil. I kind of really want this to finally work. Yep, still smells exactly as bad as I remember. Would you look at that? No trace of galling at all. I'm actually quite impressed with this oil. The other cutting oil wasn't able to produce anything nearly this good in stainless. And I'm sure that at least one of you has been waiting for me to actually screw something onto the thread. Your patience has been rewarded. With these tests, I've pretty well covered the range of materials I expect to cut with threading dies. The holder is not my prettiest work, but it more than makes up for it in functionality. I hope you learned something from the hoops I had to jump through to make this work. And if you decide to build your own, have fun.